Hi, I'm Vishal Karthik. I'm a senior Gen AI developer, and today I'll be walking you through an agent core memory demonstration. We'll be building a culinary assistant agent with self-managed memory and citations. The key concept we are trying to solve here is the provenance issue. That is when your AI agent remembers something about the user, but you can't really trace it back to where it actually learned it from. And we are trying to solve that problem today. I have a Python notebook ready with the architecture and the code. So let's jump into that. All right, so let's dive right into the code. I have the notebook open over here, and I want to start with why we're actually building this. So look at this scenario. You've built an AI agent with memory. It remembers user preferences, past conversations, important facts, but then your user walks in and asks, hey, why did the AI recommend sushi to this customer? Or where did it learn that? And you're stuck. You have no idea because AI is a black box, the memory especially. So this is the provenance problem. Traditional memory systems store what the AI knows, but not where it came from. And in production, it creates real issues. So there's no audit trail, means cannot explain the decisions AI makes. Debugging is a nightmare. So you can't really pinpoint where the wrong fact actually came from. Users start actually losing trust in your AI. And if you're in a regulated industry using GDPR, CCPA, they might require knowing your data sources, and that's a problem. So today we're going to solve this by building a memory pipeline that traces every single memory back to its source. Let's look at its architecture. Here's the high level flow. User has a conversation. Uh, Agent core detects activity, and in our case, it's after three messages, and it saves the conversation to S3 as the source of truth, and fires a notification through SNS to SQS, and then to a Lambda function. And here's the key: our Lambda function is our custom code. We control what gets extracted with Claude and how it's structured. And most importantly, we add the citation metadata. So every memory carries its birth certificate. Let's get into the code. Step one is just installing dependencies. So Boto3 for AWS, Strands Agents for our agent framework, and the Bedrock AgentCore SDK. Then in step two, we import our utilities. I've got a helper file called awsutils.py. I'm not gonna explore that in detail, but it's in the repo if you want to check it out later. And then there's the infrastructure creation. We build the AWS infrastructure. There's the S3 bucket first. This is where the agent core stores conversation payloads when the triggers fire. So when it detects enough activity, three messages, it packs up the conversation and saves it here and sends a notification with the S3 location. There's also 7-day lifecycle policy, so all payloads are removed, keep costs down. Then there's the SNS topic. It works like a broadcast system. Agent core publishes, hey, there's more messages to work on, and the SNS routes that to the subscribers. That is the SQS here. And why do we need SQS between SNS and Lambda? So there are three reasons. There's the buffering, if and when the Lambda gets busy. And there's also automatic retries on failures. And you can also add dead letter queues for debugging later. So this is the production best practice. We create two IAM roles, one for agent core to write into S3 and publish to SNS, and the other for Lambda So it lets it read from S3S, process SQS messages, and call Claude through Bedrock, and finally write memories back to AgentCore. There's a 10-second waiting time because IAM propagation takes time. And after that, the Lambda function, the heart of the custom memory. Our Lambda downloads conversations from S3, sends them to Claude, extracts preferences and facts, adds citation, and stores everything back. You'll notice that it's building a Boto3 layer because Lambda's built-in Boto3 version might not have the latest AgentCore APIs. And then we connect SQS to Lambda. So this is what actually triggers our function when the messages arrive. But let's dive into the Lambda function. So this is where everything happens. The code is organized into three main components, classes here. First is the notification handler. This handles incoming SQS events from AgentCore. So when a trigger fires SQS message, contains metadata involving job ID, memory ID, strategy ID, and the S3 payload location. So over here, you can see that it parses the nested message structure, SQS wraps SNS, which wraps the actual payload, and then downloads the conversation from S3. Then there's the second component, the memory extractor. This is where we customize. Our custom extraction logic is inside this class. Extract. Okay, this look at the extract memories method and the prompt over here. We build a text representation of the conversation, and then here's a prompt. We tell Claude to extract user preferences, interest facts from this conversation, and to return a JSON with content type and conference score. So you can customize this prompt for your use case. So for our culinary assistant application, we focus more on food preferences. So for a healthcare app, you might extract medical history or something. For an e-commerce application, there's purchase intent to be extracted. So this is the power of self-managed memory. And now to the key part, the citations. So let's look at format extracted memories. So this is what the citation includes. There's a session ID which says which conversation, actor ID to represent which user, S3 URI to point to the original payload location, job ID to represent which extraction job actually created this, and a timestamp to represent when it actually happened. And then we append a human readable citation to the content itself. Yeah, you can see that over here. It'll look something like this: citation extracted from session ID, actor ID, from source the S3 location, from job ID, and finally the timestamp along with the content. So the final component of Lambda, the memory ingester, this takes memories and batch creates them in AgentCore. We use the batch create memory records for more efficient API usage, because we sometimes might, most of the times might extract multiple memories from a single conversation. So batch create is much more efficient. And finally, the Lambda handler, it orchestrates everything, parses SQS event, downloads from S3, extract memories with citations, ingest back into AgentCore, and returns a summary. Let's go back to the Python notebook. Okay, over here we see three strategies. There's the message trigger count, so which fires after 3 messages. The token trigger count, which we've set to 500. So the trigger to the pipeline fires after 500 tokens. There's the idle timeout of 300 seconds, so it fires after 5 minutes of silence. And there's the historical window size set to 5, so we include the previous 5 messages for context. So any one of these 3 can trigger the pipeline. And memory creation here is asynchronous. So we wait for the memory to become active. So usually takes 1 to 3 minutes. Here we can see that it took us 2 minutes 50 seconds. So 3 minutes is a good time. Now finally we move to testing. So we create 6 test events. Since our trigger is 3, the pipeline should fire twice, 1 to 3 once, and messages 4 to 6 another time. And then we wait 90 seconds in total for our whole pipeline to run. So the AgentCore triggering to finally the Lambda pushing the formatted memories to AgentCore back. Okay, finally, moment of truth to check if we've actually solved the provenance problem. So our question to be answered here is, where did the AI learn that the user likes sushi? So let's get it. You can see that it all went great. Yep. Well extracted memories. So this is how the memory is actually stored, the memory itself, and a citation with the metadata involving session ID, user ID, source of the S3 bucket, and job ID, finally including the timestamp. So there's no more black box. We do know when the user actually said that they like sushi, and not just that, you know, that they like tacos too. Everything we have provenance, so we can trace this memory directly to the exact conversation in the S3 bucket. So if there's ever a question about where a memory came from, we can pull up the original payload and see what exactly the user said. Yeah, also we can also do a semantic search, something like what kind of food does the user like, and we get answered 5 relevant memories. This is a top case search, so we only get 5 with your citations. So finally we bring this all together with an actual AI agent. We create a culinary memory hooks class that implements the Strands hook provider. So on every user message, this hook takes the user query, searches our memory for relevant records, and injects the result from the searches as context into the conversation itself. So instead of letting the agent go over the memory, we do it actively and deterministically. And we format it in a way that like this. Yeah, we push the user's known preference along with the user's question to the LLM model. So Then we create the culinary assistant with our memory hooks and a system prompt to explain its role. Let's watch what happens when we ask the question. What should I have for dinner tonight is the question. And it goes, yeah, as you can see here, that with the hooks, there's a search that's happening. And along with that, there's 10 memories injected as context. The 10 memories that come from your top K search that we specified in the hooks. Yeah, over here, this top K 10. 10 is a standard value. It's usually 5, but since we have more than 5 memories over here, I've chosen 10. There's 10 memories that's injected as context. So based on our known preferences, the AI agent has figured out that we like the 6 food items, and it makes recommendations based on that. Another question involving a date night, and we get suggestions based on our preferences again: sushi, pasta, tacos, or pizza. So problems solved. uh, we know exactly where our memory comes from. We can trace it back. We have an answer to why did the AI say that with citation. And to go over the architecture once again, it flows from the user conversation to AgentCore, which triggers on 3 messages, stores to S3, notifies through SNS and SQS, invokes our custom Lambda function that extracts with Claude and attached citation and stores back to AgentCore memory, which our agent retrieves later with full provenance. So for production, you'd add dead letter queues for failed extractions, CloudWatch alarms for monitoring, more sophisticated extraction prompts maybe, and memory consolidation to merge similar memories, and the structured citation metadata in separate fields rather than an embedded text like we did here. And finally, this cleanup, I have a utils function that cleans everything that I've created earlier in this Python notebook, saves on AWS charges. All right. The full code will be in the repository linked below. The notebook, the Lambda function, and the AWS utilities for Kit. Customize extraction prompt for your use case and solve the provenance problem in your AI systems. Thank you.